So we've got a little video to wake everyone up, at least for myself.
That's the opening. You can make airplane wings all day long, but it's not nearly as exciting as making luge sleds all day long, which is what I do for a living. I'm the technical director for USA Luge, and we've partnered with Stratasys for a couple of years now, and hopefully with the projects we were lining out last night over some good Texas barbecue, I think we're going to be together for quite a while doing projects. But so what we've done, and if you look right around the corner, there's a black luge sled over there, sort of toward the boat hulls, right beside the shark. Looks like the shark's trying to eat the sled. That is actually a sled. That's one of our Olympic sleds that was built with 3D printed parts from various processes that we did with Stratasys going into the games. And so what our little presentation is going to be about is that process. If any of you were at the keynote the other day, the opening keynote I spoke, it was sort of the 20,000 foot level of what we did. We're maybe going to dig into the weeds a little bit deeper today, so if you have questions about exactly the processes or how they worked or how they didn't work or whatnot, feel free to ask the questions at the end. Please, we're counting on lots of questions. So on my end, again, you saw luge. The little sled fits underneath a person, goes down the track, 80, 90 miles an hour, 5 Gs, a lot of engineering. It doesn't look like much, but there's a ton of tech in there when it gets into, looking at the engineering, the torsional, the vibration, the damage, all that stuff. But to me, that's a luge sled. That when I look at a luge run, that's to me a luge run right there. It's sort of the Matrix thing. What I used the other day as the analogy is sort of like the binary coming down in front of me. That's how I see a luge sled coming down the hill. It's just looking at data, looking at numbers. How is it working? How is it running? What can we tweak? We censor the stink out of them in the off season. We do a lot of wind tunnel time, all of those kinds of things. And here we are with one right here. The doubles. Now there's one man, or I should say one person, because we have men and women who compete in singles, and then doubles. This is doubles, and it's doubles is where a lot of the technology that we were using with Stratasys in the process comes in, because as you can tell, it's a small little sled. You don't have a very big build envelope. It's not like a NASCAR where you have a big car around you and a lot to tweak. You have only a little bit in here to work with. And you've got all these body parts that have to fit and conform, and aerodynamics. We are timed to the 1/1000th of a second. We were the first Olympic sport to go that fine. Others have followed up since then. But we're timed to 1/1000th of a second, so little gaps, little things matter at that.
How tall are the athletes? Are you looking for a certain height?
The athletes in doubles, the bigger man is on top, so the bigger person goes on top, the smaller one on bottom. It has to do with some of the dynamics of how the sled is set up and the balance point. It gets into a lot of physical properties of how the sled actually works as it's coming down the hill.
Do they have to be under 5'6"?
Nope, no, there's no regulations. In fact, the top man there, he's Jay Kearns. He is probably about 6'2", 6'3", maybe. Anthony, his bottom man, is probably about 5'9", maybe. So in doubles, you end up partnering a bigger guy and a smaller guy together. And that's the nice thing about luge is there is no one body size. In bobsled, you'll see they all look like big old linebackers because they are big old linebackers. And that's what they need. In luge, it's really more about what you have, or about what you can do with what you have, not just being big, but you can be small and really good at the sport as well. So we have to fit all these parts. It's very organic in design, and it's very unique to each individual sled. So one of the parts that we did a lot with here was this top, what we call the tower. The bottom man's legs come through the bottom, the top man's legs there. It's all got to fit. Doubles is horrible. It's an engineering nightmare because it's not twice as complicated as singles because you have two people. It's exponentially more complicated because you move one handle and it's like, top man's like, oh, that's great. And all of a sudden the bottom guy's like, yeah, but that's poking me right in the leg. And so you're always having to push and play around things. And so this top tower, it's a very organic in design and how it comes around. And so what we do is the coaches, again, and the coaches, they know what they want. They know what they want to see. But these guys aren't CAD designers. So they're not going to get on a computer and design something, but they can make it with their hands. So they'll make a prototype, they'll make mock-ups, we'll put it, here we are in the San Diego wind tunnel, testing it, because it doesn't help you if you make a new part that isn't better, and ultimately we want to be better. So here we are in the wind tunnel testing it to seeing if it's better. And if it works out to be better, now we're in the wind tunnel in the middle of the summer, and this part has to be on ice, ready to go, with the athletes comfortable with it by mid-September. So we have a pretty quick turnaround time, along with everything else we're trying to do to get these things done. And that's where David comes into some of the process of things that we make them with.
Yeah, so we have a little bit of a refresher here today. So as I said, I'm an applications engineer. I'm in the composite solutions group at Stratasys based out of Minneapolis. So for a little bit of context, we focus on manufacturing applications. So I'm a part of a small team of 4, well, and 5 including our manager. And we focus on printing composite layup tools, sacrificial tools, and actual composite structures. So I met John at IMTS 2 years ago. He was walking through the booth going to Starbucks. I said, hey, stop. And he found out that we can print composite tooling. And it's relevant because the sleds that go down the track are made out of composites. So what is a composite? For those of you that don't know, for the discussion today, it's essentially a combination of a fiber or reinforcement, so carbon fiber, glass fibers, aramid fibers, and then some sort of matrix. So an epoxy, a polyester, even thermoplastics such as Ultem and PEC or PEEK. And when you take those two and you combine them, you add heat and pressure or a chemical reaction, you get very strong, very stiff, very lightweight parts, which are fantastic for a variety of applications, as I'm sure you can figure out: aerospace, high-performance automotive, and
high-performance sleds.
There you go. So I have an example right here to pass around. This is actually from our booth. If you haven't seen it, definitely swing by. This is actually a sandwich structure. So the tool that I'll pass around in a minute was used to make the composite top and bottom, and then we actually have a printed core. So John, if you'd be so kind as to pass that around to everyone to see.
Work it that way somehow.
So that's the refresher right there. You're all experts now. But to make a composite part is actually a very tedious process. So right now the way the market is done is the overwhelming majority, especially in aerospace, which is where I focus, it's almost always metallic tooling, aluminum, steel, and Invar, which is very expensive. Or you can also do FRP tooling. So that's actually a tool or mold made out of a composite material. So you imagine you need to print a master and then you lay up a part on it and then you use that part to make the other part. It's a little confusing, but once you see the process, it makes a little bit of sense. So, but the point here, there's a lot of pain points, as John will attest on the next coming slides. It's expensive, long lead times, and if you want to make any design to the part, so that part that's being passed around, if you might want to make any little tweak or design, you have to start from the beginning and make a new tool or a new part, and then you have to do all of the other processes that are involved. So it's expensive, long lead times, and it affects people like John because they can't tweak the sled design. So if an athlete says, I want it just a little bit different here, John has to go back and make the whole sled himself, which he doesn't have time for. So with additive manufacturing, specifically FDM, which is one of the premier technologies for this application, you can solve a lot of these problems. You can print the tool typically in hours or days versus weeks or months at a fraction of the cost. It's really great for low volume, high complex tools. So in John's case, he needs one sled to fit one athlete. Perfect. If you want to get into tooling that's going to run for thousands of parts, you may want to stick with the traditional process, but there's a great fit here, as I'm sure you've all seen at the show with additive. There's fits for every single application. So the tool I'm passing around right now, this is actually made out of Ultem, which is a high temperature thermoplastic. This is the tool we used to make that part over there. This printed in 14 hours. Pretty straightforward, and it's really great for one-off parts. It'll go up to 350F at full autoclave. And so right now, we have examples of this all at our booth. So we're able to print high temperature thermoplastics like the one being passed around. We're able to print sacrificial tooling, which is if you have a trap part like a duct or something, you can wash it out or dissolve it. And then you can print the whole coordinated tooling family. So the trim tools, drill guides, cores, all the stuff that go along with making the composite part. To show you the power of this, or an example, like I said, I mostly do aerospace. We did this with Dassault Falcon Jet. So we took their tools, we redesigned their tools. So this is their existing tools for the interior cabin of the Dassault Falcon, which, I don't know, does anyone here have a private jet? No? Maybe?
yeah,
John's got Luge pays very, very well. So we redesigned their tools. So you can see right here we have almost a 90% cost reduction and time reduction when you just do a few tweaks to allow for the principles of designing for additive. So that's exactly what we did with John and his team. So I'll hand it back off to him.
Right on. So yeah, so again, we're not high volume, okay? We're not producing 10,000 luge sleds in a season. We wouldn't use those in my lifetime. But we do need to make them unique to each team and each athlete. And so in the past, what we had done is sort of your standard old school sort of hard polyester mold like that. And what that did is it took so much work to make those, and the complexity of the part. If you remember that little tower I showed you, there's a lot of shapes to that you end up with multiple part molds. Some of them in the past have gone up to 6-part molds for making one part. And that was causing us to be one size fits all. Okay, well, we make it basically so it fits basically everybody, and that's good enough. But that really wasn't good enough once I started walking through IMTS and saw what some of the additive manufacturing can do with a couple of specific products. And one of them is the washout that David was talking about, the ST130 that Stratasys uses. So what we can do now is, as you saw at the beginning, we can make the shape of the part, and so then you add in, and this is another section of the world that's moving quick, is 3D scanning. So we make the part. The coaches make what they know what they want. They can see what they want. We 3D scan it. With the 3D scanner, that gets thrown right into, a CAD program. If we need to make some little tweaks, some little cleanups, we can, from the scanning, and then zoom, and then that gets thrown right to the printer, and you print the part. It becomes that easy to make tweaks. And then if we have a team say, oh, well, this one doesn't fit, we need a little bit more like this, the coaches can just rework the part for another team. We scan it, we throw it off to the printer, and you've got a whole new mold.
And so this is the tool we actually printed for him. It's printed out of ASA, which is
the mold, by the way, is the white thing.
Yes, this is our colleague Bruce. I want to focus right here. Go Twins! Anyone from Minnesota? Go Twins! Yeah, there you go. All right, you betcha. So this is the mold we printed. The requirements were low temperature, low pressure, so we were able to use an ASA thermoplastic, which is our commodity-grade thermoplastics, and we used our thickest tip size, so it's a T40 tip, so it's a very thick bead. So we were able to print this tool in 4 days for a cost, if you owned our system, right around $5,700, which compared to the normal process, you can...
The other molds that we'd been making were more of your standard Ren board, machined-out Ren board layups with the gel coat polishing inside. Those are costing us around $14,000 a piece. It was taking us, from the time that we came up with the design to the time we ended up actually getting the finished mold, it usually was about 3 months.
But wait, there's more.
Oh, yeah,
the next slide.
but there's more.
But wait, there's more.
Yeah, exactly. And we get the Ginsu knives. Because it was so much quicker and so much faster, we could throw in some new design concepts, which was to actually make it adjustable. So we had removable leaf. We found a point in the geometry where we could break it and throw in a removable leaf. So if we had a doubles team that was a little shorter or a little longer, we built right into this bottom piece of the mold extension pieces so that we could extend the mold that way and make it even more functional, because by doing it all on the CAD, it was so much easier to just sort of create that. So we're like, wow, this will be ready in a couple of weeks? Well, why don't we do this? Because we're saving so much time.
It was surprisingly easy to do. And so to join it together, if you want to go back one slide, so what we did for the joining, which we get a lot of questions about this, is we just did a tongue and groove joint, so nothing crazy. We added about a 5/1000 clearance between them, so we just dry fit them together. You can see how it's broken down for print time, so obviously the front was the biggest, and then as we need to do more, we can adjust the leaf right here. And then you just sealed it with, you just put a tape around it, right?
It was just a simple vacuum bag. It was a wet layup with a bag over it to get the compression on it. And that was, I think that's what it was. I don't think they did a vitamin. I think it was a wet layup.
Yeah, usually there's some sort of hiccup.
Yeah, exactly. Wrong button. So again, coming back to this complex tower piece, this is where we're going. That bigger mold was more for this bigger pan area here. This big complex part here. that is when I'm walking through IMTS and I saw David, that is where my brain instantly went to, because that is the complex shape that we have right there. And to make them all, and that's the part that needs to be unique for each team, really unique for each team, was this big complex piece right there.
Yep, so this is our sacrificial tooling material. We call it ST130 because it's sacrificial tooling and it goes up to 130
Oh,
Celsius.
that's what the ST stands for.
Huh?
I never figured
There
that
you
out
go.
until just now.
Clever, right? It's great for sacrificial tooling. It's completely soluble in a solution. It's an alkaline solution, so a sodium hydroxide. And so what you do is essentially you print the master, you do some sealing processes around it, you sand and seal it, you lay up your part and cure it, and then when you're done, you put it in the tank right there. So you can see on the right-hand side the process. We also have a patented infill, which actually encourages structural integrity from the autoclave or vacuum bag, as well as encouraging turbulence as it washes through. So we call it the permeable triangle on top, and you can see, so what it does is it encourages faster dissolution of the material, which is exactly what we did for John's part,
Right.
the doubles tower right there, which was a surprisingly complicated part. When he sent it to us, I was like, wow, what are we getting into? But again,
And the open part for the wash through, it was all sealed all the way around except the piece that's sitting here on the bench. That was the open face that everything was washed out from.
and again, we printed this in less than 2 days, and then you just did a simple sanding operation on it,
Yep.
and then a sealer, and you're able to make a couple of parts.
And then we laid it up with glass, and we sent it off. They washed it out. It came back, did some little cosmetic cleanup because my bagging job wasn't as good as I'd hoped it would be. But just a little bit of quick bondo. They even printed a cut tool for us so that we could trim it out, so that it would then match up perfectly with the bottom. And there we have the part. So this was unique to, this shape in here ends up being unique for each of the teams. And we can adjust it on the fly, and it's just a matter of printing up that new mandrel, doing a new wrap, and it literally, we can change as needed within a week.
Yeah, and that's a great point. I mean, you were commenting in the keynote, the human body is not mirrored perfectly in half, right?
Right.
So if one leg is a little bigger than the other, one side of your body, you get a little heavier, you get a little skinnier. It's nice to have that customization and freedom.
Right, because these were being designed by your typical CAD design. So a few splines, a couple arcs, you connect it all with lines, and then you mirror it, right? So everything looks nice and symmetrical. That's how engineers think. Nothing personal, Dave. That's how engineers think, and that's how CAD designers work. Is everything is even and symmetrical, but the human body is not symmetrical. So if one of these sides has a little gap, if this side fits great, but this side, the leg is a little different, and you have a little bit of a gap. 1/1000th of a second. Remember, the sound of a snap is 1/100th. We're 1/1000th. Okay? And so that little gap matters. And so that's why these unique shapes, these very organic shapes in the sled have to take place. And the adjustability for it, or as teams change, top man quits, bottom man quits, we can then adjust the sleds on the fly for them.
I should comment too, we originally designed these sleds for prototyping, just to test them out in the wind tunnel, but you actually ended up using them in the Olympics.
It was a test. We'd never done this before. We hadn't done this before. They hadn't done this. There was a lot of learning curve involved in this, a lot of sending parts back and forth because we had to outsource the scanning and then get the files and move things around. The whole process took 6 to 8 weeks to receive the parts, and that's first time ever doing it, solving all the problems along the way of first time you ever try to do something, all the communication pieces across multiple different partners of ours, and shipping time, and it still was only 8 weeks, 6 to 8 weeks. So I was really happy with it. Now that we've solved some things, it'd be even faster next time. There's another part that we use that, again, it's a very complex part. If you look at this part here is called a Kufen, okay? You now have a German word in your vocabulary. If you have Gesundheit, now you now have 2 German words in your vocabulary. But this front part, you can see where the legs are, again, is very unique and it's very functional. That's how you steer the sled. So it's important. It's like having a steering wheel that you can reach. Okay, it's good to have a steering wheel you can reach. And it's very unique to each team. Some of them like to feel a little wider, some a little narrower. It matters in the wind tunnel. There's some aerodynamic components to it. So what we can do is changing on that front horn part where all the feet are, that's just a basic ABS printed part. It's a hollow fill part. So it's sparse filled, there's weight reduction in there. But we just take that and we do a composite wrap over it. A couple layers of a biaxial sleeve carbon sock, a little resin, a little vacuum, and you've got yourself a part that then gets attached to the rest of the body Kuvin. And if we want to change it a little bit, it's just, you go into a CAD program. Okay, we want to do that. That's what the coaches are telling us. We need to move it a centimeter and a half. We can see where things overlay. We can just sort of work it around in your basic, in a CAD program. We can then take that, and a lot of these materials now are getting some really good FEA numbers on them. So you can just take the material and pull it up in your basic, FEA analysis software. So we can do the strength analysis, the bonding analysis, one part to the next, all of those things, because all this 3D printed material now is really, the science behind it has gotten really good. And we can produce a part and change it on the fly. Again, it's a matter of a couple days of printing, some composite work, and it's changed. And then finally, on this part, this is a single sled. As I said, there was doubles and singles. This is a singles. And on this sled, this piece right here is a 3D printed part. One thing, it holds the athlete in place, because if you can imagine going down the track at 80, 90 miles an hour, 5 Gs, going up and down, bouncing around, you probably want to stay in place. That part holds you in place. It's actually a crotch piece so that you know that you're positioned right on the sled. There's also a lot of tech dealing with how the sled works that's hidden under there. So it has to do with some technology protection as well. But we're like, well, it's pretty. Why don't we make it sort of fancier? As somebody said the other day to me, it's like, I can't believe you worked the word span-dangled into your presentation, but
Yeah,
that's
that was
a span-dangly part right there because we could. It's a polyjet printed part. It has a lot of color, so it's the Olympics. Why not make a little red, white, and blue span-dangled on it? And so that's what we did. And that's, again, getting back to the polyjet with the colors and stuff you can do. Why did we do it? Because we could. It was fun to do. So that's why we did it, for no other reason. I mean, it could have been a boring gray part, which is essentially what it is. It's just an STL file of a part that was made and designed, but instead of designing it in black or, what is it, T-Vero black or whatever, one of those colors, we jazzed it up a little bit. So that's some of what, that's some of the process that we have and that we've gone through.
And we've just reached the tip of the iceberg on this. I mean, it started out with just playing around, and again, after the barbecue last night, we've got some serious stuff coming down the pipeline.
Yeah, and this is the stuff we can talk about. I mean, this is a highly competitive world. This is 1/1000th of a second. We are out there spying on each other. If you think that this is not a world of the clandestine spy, you are wrong. True story. This is going into Sochi a couple years ago, a few Olympics ago. There was Sochi. Everything that went to Sochi had to go through the Moscow airport. Okay, there was no way into Sochi directly before the Olympics. Every country in the world going to Sochi, whether it's a ski team, bobsled team, luge team, everything had to go through Moscow. Going through Moscow, like in all airports, things get X-rayed, right? I mean, you put your bag on, they put it through the X-ray machine. You're putting a luge sled on, luge sleds go through the X-ray machine. We found out the Russians had been X-raying all of the sleds coming through the airport.
Awkward.
It is a competitive world, trust me. And we found out that our sleds and the German sleds had been X-rayed and had been torn apart by the Russian engineers on our way into Sochi pre-Olympic.
So there you go.
So yeah. So anyways. And that came to light in an interesting way. So there's a lot of tech that we are working on, just like in aerospace, just like in automotive. There's stuff that's being held, but there's cutting edge stuff. There's a lot of really cool technology happening out there. And to me, the big real takeaway is incorporating multiple disciplines. You incorporate the 3D scanning, which is getting so good now, in with the 3D printing technologies of different materials. And then combining that with some traditional composite work, and I mean the sky is really limitless on what you can design and make when you come up with those, and the way that you can incorporate it. It doesn't just have to be on a CAD program. You can do, as I said, our coaches do literally hand sculpting of parts we scan it and create the parts at a very high-end level, very high tolerance because of those technologies.
There you go. Couldn't have said it better. If you got questions or comments, emotional outbursts, we'll be around.
Yeah.
Yeah.
Does SLED have to be approved for use by some international?
No, it doesn't have to be approved. We do have some rules, so there are some things we cannot do. So there are some points on the sled.
An engine on it.
Yeah, can't put an engine on it, no rockets. There are some certain connectors where we can't put materials because we've done that in the past. In 2002, where the steel blade attaches to that coof and that runner, there was a lot of dampening material put in there. They decided that was illegal. It obviously was creating a benefit. So if it created a benefit, they said, no, you can't do that anymore. There's a big battle in the sport between the purists and the techno geeks. And the purists say, let's just keep it basic. And the techno geeks are like, let's go have some fun. And so there's always that battle. And on that one, the purists one said, no, let's take that material out. And so there's a lot of give and take. But in general, the sled has certain dimensions that it has to fit in. So there's a basic building box that you have to stay in. And there's some weight regulations. It can't be over a certain amount because the heavier you are, the faster you are. So there's an upper limit of weight that you're allowed to be. But essentially, within some of those parameters in the rule book, you're allowed to do quite a bit.
What is the weight?
The weight on a single sled, it's a minimum of, it gets a little complicated, but for the simple sake, it's between 21 and 23 kilos. 21 and 25 kilos, with 23 being the mid-range, and then the rules are governed off that. And on a double sled, it can go up to 30 kilos. And again, and everything we do in our sport, it's all metric. So everything I do, machining, everything is all in metric. And so it's a lot of fun trying to find metric tools in the US and some of those things. It's a little bit of a challenge, but everything, because our sport is a European sport, our team spends so much time in Europe that if something breaks, if something happens, they have to be able to just go out, they have to get a part, find a part, do something, and everything is metric. I don't know how to machine in SEA. I don't understand how to compute a tool path if it's not metric.
Question?
You guys mentioned a little bit about the soluble support material
Mm-hmm.
and how it can survive in an autoclave. What have you thought about, or what have you done in regards to looking at pre-pregs or in autoclave purified materials that you use?
So he asked about...
Yeah, you can handle the
So if
technical
I understand,
aspects.
so you're asking about experimenting with pre-pregs using the sacrificial material. So it works. We do it right now. We have a lot of anecdotal data with a lot of... It's mostly aerospace, but... as long as-
What's the temperature range of the ST?
So the ST-130 will go up to 250 F at vacuum, 210 F if you are going full autoclave, which is around 130 C, ST-130. If you have to go higher than that, we do have a other sacrificial material. It's not soluble, but you can embrittle it with acetone. So if you essentially saturate it with acetone with a spray bottle, it becomes like a graham cracker almost. And you can physically remove it out of the part that way. I should also do my shameless plug. We have design guides on all of this too on our website. Two of them, one for printing layup tooling and one for printing sacrificial tooling. They're about 100 pages each, so if you want to take a nap on the plane, I recommend downloading them beforehand. Great question, though.
And for us, what I ended up doing with that, just because of somewhat of the limited shop that I have and some of the time crunch I was pushing on, that I did as just a wet layup. That was a wet layup with a bag, with a vacuum on it. So there wasn't a temperature and an autoclave pressure issue with it, because there was just a wet layup with a basic, just a vacuum line on it.
Any other questions? Or
Go for it.
yeah, go for it.
So what would you say for success? What percentage is the craft, the vehicle, and what percentage is the athlete? Previous to success?
It's, well, obviously, and I think it was Michael Phelps or somebody at the Olympics said, because there was a big controversy about their swimsuits one year, and he's like, well, I've thrown a lot of swimsuits in the swimming pool, and they don't seem to go very fast. So there is an athletic component to it. Yeah, same thing. You can put a sled down the track, and it's not going to go down faster without, well, actually, I have seen some sleds that might go down faster without their athletes, but in general, the athlete does put the sled down the hill. And so knowing how to drive lines, that athletic component, there is definitely a part to it. But when you get to those upper reaches, when you get up into that upper echelon of the Olympics, you know, your top 10 athletes in each discipline, the skill level is pretty much comparable. You know, what they can do, what they're able to do, the knowledge that they have is pretty much almost, I'd say, dead even. And so what then comes in underneath is what's under them. You know, what is the technology and their confidence that they have in their technology under them. It's such a mental game. And so that's where, you know, making sure that it fits them right so that they don't have that little poke just, you know, all the way down the track. You know, it fits them right. It fits them well. That gives them confidence. Having it, you know, the lead times that we talked about, having it in time for them to see it and get comfortable with the process that made their sled goes into a whole sports site category that we could, you know, that's another whole sports
We weren't even
conference.
done printing the first sled, and John's already texting me for new designs and stuff
Yeah.
after the fact. So it's
Yeah,
later in
so
the cycle.
there's that component. So there is a manufacturing component that does affect sports psychology when it comes to sports, having that lead time and the athlete's comfortableness with the process, and they're like, oh, that's pretty cool. I like that, and so that matters. And so yeah, a lot of the technology, as an example, in the doubles from Sochi to Pyeongchang, we cut our deficit in half. If you look at the average results of where our doubles ended up in the placements in Sochi to where they ended up in Pyeongchang, we cut that deficit in half. We averaged in doubles about 12th in Sochi, and we were 6th and knocking right on the end. And when I say 6, that's still pretty far out. Remember, 1/1000th of a second. I have seen races still tied after multiple runs to 1/1000th of a second. So by placement, it may not sound, the time gaps are very small. So it did a lot. We really closed the gap on that, and with some of the designs that we were sketching last night over some awesome barbecue, I think we're going to be closing that gap a lot more.
Anything else? Good?
Keep going.
Yeah.
So you mentioned the mindset. Is there a certain personality type that is attracted to luge?
Wallflowers need not apply. What we do for recruiting is we go out and we actually have beginner sleds, not Olympic levels, so beginner sleds. So we go out and we take the ice blade off and put a wheel assembly on in the summertime. And using gentle hills, we have kids come out and give it a try to see how they like it. And it's a basic 2-hour clinic. We teach them how to steer left, how to steer right, how to stop. And by the end of the clinic, we have them going through some orange cones. The best kids from there then get invited to come and try it on ice. And then from on ice, it's just a constant sort of, you know, weeding out process until the end of the season. And then they get selected into a program, and then we do it all over again. And so one will naturally select itself. You know, kids either on wheels or their first experience on ice will be like, that's a little weird. And they're done. And that's fine. You know, as I say, everybody has a sport. You know, just keep searching, you know. I've had kids that absolutely hated luge, and they're now national level fencers. You know, it's like, great, just keep searching. You know, there's a great sport out there for everybody. But the ones that, if you stick in it, it's that rush, and it's just the ability to, you know, and the thrill of it. But the one thing we have noticed is that the kids that sort of have the, hey, dude, you know, attitude, not to pick on snowboarding, but I will, you know, that kind of attitude, generally end up not doing too well in luge because it is fast, and you can't be just sort of the hang it out there dude at 80 miles an hour. You really actually have to, it's a thinking man's game. You really got to work it, and you got to be very subtle with it, and you got to be very collected when things go wrong. You just got to be able to fix it slightly. So it's somebody that likes the thrill, but they tend to be very analytical as well. So that's sort of where it goes.
Wayne, I'm going to sign you up. Yeah?
Yeah.
What's the name of this barbecue place you guys got?
Oh, well,
Shout out to Railhead.
yeah,
Railhead Barbecue. I
Railhead
went there
Barbecue.
twice in 2 days.
Yeah, it was pretty odd. The second I walked in, I'm like, oh, you picked a good
Well, you
spot,
don't have good
David.
barbecue up in Minnesota, I'll tell you what.
No. And,
Yeah.
yeah, and I don't know how we're doing on time, but the one other thing, and I'm just, my shameless sort of plug in here for things is, with what, because I work with kids, not only do I design and build sleds, but I also coach. And so I have a whole team of kids that I work with that range from 8 years old up to usually about 16, 17-year-olds. And I work with them, train them, travel around the country. I've traveled around the world with them. and this technology is really interesting. And I got so jazzed, and I'm a retro grouch, okay? I still have a hardtail mountain bike. It took me forever to get rid of my long skis, okay, my straight skis. If you're a skier, you know what I'm talking about. I am I still loathe the day that Mac went to Intel, okay? I liked my Mac only software. Okay, so I am a retro grouch, but I've totally bought into this whole process and what this additive manufacturing and the potentials in the future are for it. And so my plug and where my brain went earlier today as I was walking around the thing is, if you're a president of a company, or if you have if you have your shop in the one-level industrial district somewhere, go back to your community and find the high school kids that have the robot club or that have a CAPS program or something, and find the kids and get them involved in what's going on, because they are the ones who are going to take the technology that you're inventing tomorrow, and they're the ones who are going to be making stuff in the future so that I can still walk when I'm 90 years old, because my knees are not that good and neither are David's.
No.
and so I implore you to, the high schools, they're not going to be thinking to go, they've got too many things to go out, but go and find the kids and get them involved. Get those kids that are in the robotics programs and that are in, some of these programs, and get them involved in high school, because they're the ones that will take the technology and run with it, because they haven't learned to be cynical yet.
Oh, no. And I should add, too, coming from being at Stratasys and Additive, let them play around with the technology, too. So Wayne, he can attest, if you don't print a ball of spaghetti in your first week of working with a 3D printer,
you're not trying hard enough.
You're not doing it right. There's got to be a little bit of flexibility there. Oh, I accidentally wasted a $10,000 part because I didn't orient it the right way. We'll just write that one off. But
yeah, but yeah. So I think the technology is great. Again, I'm a retro grouch. I've totally bought into it. We're using it on our sleds. We're really advancing our sport. And the places I see this going, just again, because I work with athletes and bodies, the whole biomedical prosthetics, robotic prosthetics with the 3D scanning, the composite tooling, and composites is just phenomenal where I think it could probably go. So please, go find a kid, mentor them, get them involved in it.
Yeah.
They're going to do great things. And then also tell them the luge coach said that so they can watch the luge on TV and bump our ratings up.
Yep, bump it up. All right, that's it. Get out of here. No.
Thank you.
Thank you.